Welcome, dear students. Today we are going to discuss about the NMR spectroscopy, nuclear magnetic resonance spectroscopy. It is a very important analytical tool to determine the structure of compounds, mainly structure of many organic, inorganic, and many biomolecules, etc. This technique mainly deals with the magnetic properties of certain nuclei like hydrogen, C13, etc. Okay, this technique involves the study of transition induced between the spin energy levels of these magnetic nuclei in a species in an applied magnetic field by absorption of electromagnetic radiation in the radio frequency region. That is, two things we have to note. For recording NMR spectra, we need a magnetic field. Compared to other spectroscopy, that do not need a magnetic field to study the spectra. But in NMR spectra, we need a magnetic field, and the light using here is normally radio frequency. That is, in this spin energy states, transition is occurred using radio frequency in the presence of an applied magnetic field. Okay, and first thing we are going to discuss about the theoretical principles of NMR spectroscopy. And first we have to know about the nuclear spin states. That is, certain nuclei have a nuclear spin I. All nuclei do not have spin. Only certain nuclei have spin magnetic moment or spin. And actually, there is no a rule or theoretical rule to analyze or to understand the spin of a nuclei. A general rule states that is, actually this spin comes from the fact that a proton has a spin of half, like the electron, and neutron also has a spin of half. Actually, the vector sum of the spin of the proton and a neutron is the resultant spin of the nuclei. For example, in the case of hydrogen H11, when there are one proton and one neutron. If the spin of the proton and neutron are parallel, the resultant spin will be 1. And if they are anti-parallel, the resultant spin is, this is half plus half is equal to 1, half minus half is equal to 0. But experimentally it is found that in the ground state, the spin of hydrogen is 1. I is equal to 1 for, so not for hydrogen. I am discussing about deuteron, that is H12. Hydrogen spin is equal to 1. In the case of hydrogen, only one proton is present. Therefore, spin will be normally equal to 1. Only one proton. No pairing takes place. But in the case of deuterium, a proton and a neutron is present. Therefore, spin will be parallel or anti-parallel, or it may be 1 or 0. But experimentally, it is found that the spin of the deuterium is equal to 1. But there is no a general rule to predict the spin is derived yet. But arbitrarily or in a general findings, it is observed that if A is equal to, if we consider A, Z and nuclear spin and some examples, you can draw a table. Okay, if A is equal to even and Z is equal to even nuclei, the spin will be 0. For example, C612, He24, O816. Fortunately, the spin of this nuclei, normal carbon 12 is thought to be 0, helium is 0, O8 16 is 0. But if A is equal to odd, Z is equal to odd or even, then nuclear spin, what will be it be? We can assume like this. That is, when A is equal to odd, then either proton A should be odd if either proton or neutron is equal to odd. If both are odd, it will be even. Okay, one of them will be odd and other will be even. Therefore, it will be in a half integral. Okay, spin will be half integral spin, like half, 3 by 2, 5 by 2, etc. Okay, for example for this type of nuclei are H11 hydrogen, spin is equal to half, and C613, the spin is equal to C613, again it is equal to half, and phosphorus 31, okay, and its spin is equal to, phosphorus spin is equal to again half. But for boron 11, B511, the spin is 3 by 2. In all these cases, spin is a half integral spin. Spin is half integral. Okay, but if the atomic mass number is equal to mass number is even, but atomic number is odd. Okay, mass number is even, but atomic number is odd. Then here, mass number even, atomic number even means atomic number odd means proton is equal to odd. Therefore, neutron also should be equal to odd. Therefore, odd plus odd. Okay, proton odd, neutron odd. Therefore, the spin will be integral spin. That is, its spin will be 1, 2, 3, etc. For example, if you consider N714, atomic number odd, mass number even, its spin is equal to 1. Another example, B510, its spin is equal to 3, like that. Okay, and this type of nuclei are generally known as quadrupole nuclei. Spin 1 and greater than 1 is called quadrupole nuclei, and spin 0, that is this type of nuclei, that is atomic number even, mass number even. Okay, spin is equal to 0. They are non-magnetic. They do not show nuclear NMR spectroscopy. They are not involved in NMR transition, nuclear magnetic transition. Only the species now we are considering only this type of species. Here the spectra will be even some NMR spectra is possible in this case of molecule or nuclei, but it will be spectra will be broad. We are considering this type of nuclei. Mainly we are considering proton and C13 in your syllabus. Okay, mainly proton. C13 is not considered in your syllabus. Okay, but C13 spectroscopy is there. C13 NMR is there. It's a proton NMR is there. But in your syllabus, we are mainly discussing about the general theory of spectroscopy, NMR spectroscopy, by considering the examples of proton NMR spectroscopy. Okay, thus a nuclei having a spin have a spin angular momentum, and this spin angular momentum is actually have 2i plus 1 orientation. All of them are degenerate orientation. That is, spin angular momentum is oriented in 2i plus 1 ways, that is from minus I, adding an integer 1 plus 1 plus 1 plus etc. minus I plus 1, minus I plus 2, etc. in like that, and I minus 1 finally I. For example, in the case of proton, I is equal to half. I is equal to half, therefore it is minus half. Plus 1 is equal to plus half, that is I. There are only two orientation, minus half and plus half. In the case of deuterium, H12, I is equal to 1. It will be minus 1, plus 1 is equal to 0, and plus 1 is equal to 1. And that is equal to minus 1, 0, 1. There are three orientations. Okay, but these orientations are degenerate in the absence of an applied magnetic field. Okay, and the nuclear angular momentum I is actually a vector. It is equal to root of I into I plus 1 h divided by 2 pi. Okay, that keep in mind. And the effect of an applied magnetic field. When nuclei are spinning, this type of spinning nuclei can act as a bar magnet or simple or a tiny bar magnet. And if we apply an external magnetic uniform magnetic field, this tiny bar magnet or nuclear spin tend to align to the applied magnetic field. Okay. Before that, we are considering the magnetic dipole moment. Magnetic dipole moment mu is actually, it is proportional to spin angular momentum. Nuclear magnetic momentum mu is oriented along the axis of the spin and is proportional to spin angular momentum I. That is, mu is equal to a constant gamma into I. And gamma is called a magnetogyric ratio, or gyromagnetic ratio, and its value is Gn E divided by 2mp, where Gn is the, it is the nuclear, Gn is the nuclear G factor, GeV you have studied in some other sections. There is electron G factor. Similar, Gn is the nuclear G factor. In electronic G factor, Ge, I think its value is 2.00 something, that value, that is experimentally or theoretically calculated. But nuclear G factor cannot be determined theoretically, should be determined experimentally, and its value is different for different nuclei. And most of the nuclei's value is positive for majority of nuclei. Value is positive for majority of nuclei, and its value is up to 6. Most of the maximum value is 6. For proton, Gn is equal to 5.585. It's a unit dimensionless quantity. Okay, then we can write the nuclear magnetic moment mu is equal to Gn into E divided by 2mp. mp is the mass of proton, E is the electronic charge or the unit charge, into I, vector I. Okay, and okay, take this here. When we are applying an external magnetic field, the nuclei will align itself to the magnetic field. Then the potential energy will be the product of the potential energy is the product of the nuclear magnetic moment and the applied magnetic field strength B0. Okay, then mu is equal to this one, that is Gn E divided by 2mp. Okay, that is mu into I into B0. Okay, clear? I think you're clear. That is mu is equal to Gn into E divided by 2mp into I into B0. Okay, but this nuclear angular momentum vector I has only a discrete orientation. In the presence of an applied magnetic field, this discrete orientation have become non-degenerate. They become different energy. Okay, and I is actually have different values from minus I to plus I, that I have already told, and I am indicating this values as discrete value as mi.